All right, everybody. Hello and welcome back to another episode of our GEO1 course. Thank you so much for being here. I hope everybody's having fun out there, both in life and with the class and everything else. I really appreciate you guys showing up and listening to these recordings and participating in this class. It's absolutely wonderful. As always, I'm going to remind you guys that I am always here and available for you as you're going through these things. I want you to know that I'm here. And if you need anything at all, I'm here. Feel free to reach out anytime. It'd be wonderful to have the opportunity to chat. With all of that said, we're going to begin our discussion of rocks today. Tons of fun. I'm sure that when you signed up for geology, you knew and you maybe even anticipated at some point we're going to be discussing rocks quite a bit. And this really is true, no doubt about it. We're going to be doing this for a little bit of time here. We're going to talk about igneous rocks and then volcanoes and sedimentary rocks and all sorts of interesting things. But that said, this really begins our journey into our rock discussion. So with that, I'm going to introduce this next portion of our modules here, igneous rocks. And note that we're going to start out this discussion describing something called the rock cycle. The rock cycle. Then we're going to define igneous rocks. We're going to break things down to talk about how we divide up or group igneous rocks, very similar to how we discuss different groupings of minerals. We also group igneous rocks in different ways. And we're going to talk about those features that we use to group and identify rocks. And then we're going to talk about the different environments in which these rocks form. Again, rocks are evidence. Rocks are evidence of environments that may no longer exist. Maybe environments that are completely different from the environments in which those rocks exist today. Those rocks represent these places, these moments in time, and our interpretation then of these rocks allows us to transport ourselves both in space and time with just a bit of knowledge about how these rocks form. All right, so let's go ahead and launch into it. Let's talk about the rock cycle. At some point, you may have been exposed to the rock cycle. My little ones were recently watching the Magic School Bus, and I overheard them discussing the rock cycle. Every now and again, my wife, who's also a teacher, I hear her discussing the rock cycle with her elementary school students, and sometimes I hear her even singing. That is, it's to the tune of "Oh My Darling," but the rock cycle. Igneous rocks, sedimentary rocks, metamorphic rocks on my mind. I'm not a singer, not at all. I love music, but I'm not a singer. But that rock cycle, right? And so the rock cycle oftentimes are defined with these three sort of main points, those points being the different types of rocks that we have: igneous rocks, sedimentary rocks, and metamorphic rocks. Each of these different types of rocks has a definition, and we're going to go through those definitions as we go through these different rock groupings in detail, but I'll give you the overall definitions for each of these rock types right now. Definitely something great to have in your notes. That is, igneous rocks. Igneous rocks are rocks which form when molten materials solidify. So if you have molten rock, and that rock cools and solidifies, you get an igneous rock. Okay? Doesn't matter what it started out as, doesn't matter its history before that moment. If the last step in that process was molten to solid rock, then you've got yourself an igneous rock. Sedimentary rocks are rocks that are made of the bits and pieces of other rocks. Bits and pieces of other rocks. Those could be physical bits and pieces of other rocks, or even the chemical bits and pieces of other rocks. They come together, they form a sedimentary rock. Metamorphic rocks are rocks which have been changed, which have had so much change that they are altered either chemically or physically in the arrangement of different minerals inside of the rock. They've been changed. such that their properties are completely different than what they originally started out as. Metamorphic rocks, it's not that they melted and changed. If they did that, then they're an igneous rock. But metamorphic rocks, through the activities of pressure and heat, we can rearrange where minerals are in those rocks. We can change them a little bit. We can mix up the chemistry there a little bit within these rocks. I give you these definitions because those definitions are what we need to know to understand the rock cycle. One thing I feel the need to share with you guys is that this rock cycle concept, this cycling of rocks, is a bit of a misnomer. That is, the term cycle seems to imply that rocks start out as one thing, and then they become the next thing, and then they become the next thing, and so on and so forth. That is not necessarily true. Not all rocks go through that step-by-step process of being an igneous rock, then a sedimentary rock, then a metamorphic rock. That is not the way it works. Rather, rocks can jump between any of these rock types through processes, physical processes going on here on Earth. That is, an igneous rock can become a sedimentary rock if it's broken down and then those bits and pieces of that rock come together to form a sedimentary rock. But an igneous rock can also become a metamorphic rock if it's exposed to intense heat and pressure, and that rock is then changed, then that igneous rock can become a metamorphic rock. And if you take a metamorphic rock, you break it down into pieces, form a new rock, that's a sedimentary rock. And if you take that metamorphic rock and you melt it down and form a new rock, it's now an igneous rock. And if you take that metamorphic rock and you heat it and pressurize it even more, it's now a new metamorphic rock. So what I'm saying there is that the cycle aspect of this, again, implies that these rocks go through this step-by-step sequence, and they don't necessarily. They don't. So what we want to know for this course are the definitions that I just gave for each rock type, because that's the foundation for understanding the different types of rocks that we find here on Earth and what they represent in terms of environmental changes through time. All right. So if you see a question on a future quiz or midterm that says the rock cycle states that we've got this sequence, and that's true. We always get this sequence. Igneous rocks always become sedimentary rocks, and sedimentary rocks always become metamorphic rocks, and then the cycle starts over again. That would be false. That is not true. That is not true. All right. All right. Awesome. And then also you're going to want to take away from that those definitions of each of those rock types, such that if I gave you the history of a rock, I said, you've got a rock and that rock was made into the bits and pieces, smaller fragments that formed a new rock, but then that rock was heated and pressurized to form and now a new rock. What kind of rock is that? You would say, well, it's heated and pressurized to form a new rock. That's a metamorphic rock. Right, if I told you then that rock was melted down and formed a new rock, now it's an igneous rock. All right, so that's the goal of that discussion. So let's talk about, we're going to focus on igneous rocks. Again, igneous rocks are rocks which form from molten materials. So what do we call that? Molten stuff, the melted stuff. What's that stuff called? Well, it goes by two names. If within the Earth, if there is molten material below Earth's surface, we call that magma. Once that magma is released onto Earth's surface, we then call it lava. Lava. So lava is that molten material that has been extruded onto Earth's surface. Magma is what it is below the Earth. So magma below the Earth feeds volcanoes maybe. And if that magma comes out of the ground in those volcanoes, once that magma comes out of the ground, it's then considered lava. All right. So a few things to know and remember in this discussion about minerals before we fully dive in is that mineral properties will be the same in any specific type of mineral independent of size. That is until we get down into that clay-sized bit that we talked about in the last lecture. When we see a quartz mineral grain in the museum and it takes up an entire table, the properties of that giant quartz mineral grain will be the same as a quartz mineral grain that is the size of a speck of sand. And so when you look at a piece of igneous rock like granite, granite is a really common example of an igneous rock. You see that it has all of these kind of colors on it, these little blebs on there. Each of those little blebs is an individual mineral grain. So how do we identify those really tiny mineral grains? Last time we talked about all those mineral properties that we would normally use, like hardness tests and maybe evaluating the cleavage pattern of the mineral. How can we do that in these really small mineral grains? Well, the answer to that is oftentimes we can't. Oftentimes we can't do those tests on these really small mineral grains. So what do? Well, again, we as geologists, we just sort of guess. Nobody questions us because we say it very confidently. I'm just kidding. That's not true at all. We know because if you remember SNOIS, right? SNOIS. Part of that SNOIS requirement for a mineral is that it has that orderly internal structure, that sequence, that pattern in the arrangement of minerals or atoms, I should say, within that mineral. And that framework, that structuring adds a new property to these minerals when they're viewed underneath the microscope. That is, if we take a small slice of this granite and we shave it down very thin to a thickness of about 30 microns or so, really, really thin, so thin that we can actually shine light through this thin slab of rock. These thin slabs of rock, we call them thin sections. The light we shine through them is oftentimes a polarized light. It is emitted from a specialized microscope where you can polarize the light, do all sorts of really fun things. And by doing that, you can make the light shine through the minerals in a predictable way. And these minerals, because of their internal structure, their atomic arrangement, they'll move and deflect and do all sorts of interesting things with light specific to their mineralogy. And so looking at these thin sections, we see properties within these minerals that are shared at the big scale. Things like biotite will still look very sheety, and quartz will look kind of globular. But we'll also see these things change colors in these specialized lights. This specialized light, we'll see in some cases the light is completely blocked at certain angles for certain minerals, right? And so looking at these things again, we can look at these fundamental building blocks and add some criteria for identifying these minerals at this very small scale. All right, so we have a whole bundle of different types of igneous rocks. There's a lot of them. And part of the reason for the diversity that we see in igneous rocks is because these rocks are made in different environments. The biggest difference in the types of environments in which these igneous rocks are made is whether those igneous rocks, whether that molten material is cooling at the surface, that is lava cooling. This is something that we would call an extrusive igneous rock or a volcanic rock. If you take those molten materials and you solidify them at or near the surface, right, that's what we call an extrusive rock. If you do that cooling, if that cooling happens at depth, maybe kilometers below the surface of the Earth, we would call that an intrusive igneous rock or a plutonic rock. So these two environments yield very different rock types. Why? Why is it that if I take a molten mass that has the same chemistry and I allow that molten mass to cool in a magma chamber deep below the surface of the Earth, why is that going to give me a very different rock than a rock that cools at the surface of the Earth? Well, the reason for it is the rate of cooling, differences in the rate of cooling that happens in these two environments. When molten materials cool at depth, they generally do so at a very slow rate. They do so at a very slow rate. If these materials cool at or near Earth's surface, they can cool at a very fast rate, seconds, right? The differences in the rate of cooling we're going to see gives rise to some really fundamental differences in the sizes of the mineral grains we see between these rocks that cool near Earth's surface and those that cool at depth. Some big differences there in the sizes of the minerals that accumulate in these two different environments. So we're going to be back and forth from this concept a number of times in this lecture. And that's because one of the first things that allows us to identify an igneous rock, that is to say something like this rock is a granite or this rock is a basalt. One of the first criteria, the primary criteria that we use to do that is the rock's grain size, or what's commonly referred to as texture. Grain size, commonly referred to as texture. So when we say texture, we're not talking about is the rock smooth or is it soft or those sorts of texture type discussions, but rather, again, grain size. Are the mineral grains very large or are they very small, right? Are they very large or are they very small, all right? The second thing that we utilize to classify or identify igneous rocks is composition. What's it made of? What is its chemistry, right? What's its chemistry? So grain size or texture and chemical composition, those are the two primary factors used in identifying igneous rocks. So here's some examples of different igneous rocks, different igneous rock textures. We can see here in the image on the left, the one that's labeled here aphanitic, we can see that in that hand sample there, in that sample of rock that we could hold in our hand, we can see that it largely consists of just kind of a uniform mass of indiscernible materials. There's no large mineral grains in there. There may be some small flecks of material that you can see inside of the rock there. Maybe just a few little shards that we can make out. For the most part, it just looks like a uniform kind of gray mass, right? The rock next to it, the rock that's listed as porphyritic, however, we can see that texture is very different. We can see areas of light colored minerals, areas of dark colored minerals, some pink minerals in there as well. And we can distinguish between each of those mineral grains within that sample. We can also see in this, the bottom image, sometimes we get this glassy texture where these materials look like glass. And again, what the difference is here in these textures between these different types of rocks, what we're seeing is differences in the rate of cooling, differences in the rate of cooling. So just a few of these textures that you're gonna want to know as some common ones. Aphanitic textures. Aphanitic textures are igneous rocks, just like we saw in the previous slide here, where the mineral grains are too small to be seen with the unaided eye. The mineral grains are too small to be seen without use of a microscope. Okay, that's an aphanitic igneous rock. A phaneritic igneous rock is one where you can see those mineral grains, right? That is, you might see this multicolored pattern on the rock, or you might see some of those cleavage faces exposed in the surface of the rock, right? That's a phaneritic igneous rock. And everything in a phaneritic igneous rock, we can see those individual mineral grains, and they're all going to be pretty close to the same size. That's in contrast to what's called a porphyritic igneous rocks or igneous rock, where the grains are of mixed sizes. Some are large, and some are very small. That's what we would call a porphyritic igneous rock. And with those different grain sizes in there, that might indicate a special situation where we see maybe some of the mineral grains cooled at different rates, right? Maybe they cooled at different rates. Maybe there is a multi-stage cooling history for that rock. So I keep talking about rate of cooling being linked to igneous rock texture or grain size. And why is that? Why is that? Well, let's first look at extrusive igneous rocks, those that cool at or near Earth's surface. That aphanitic igneous rock texture that we've seen on these previous slides and discussed is commonly associated, is directly linked with our extrusive igneous rocks, this fine grain size. Why? Why does rapid cooling result in this fine grain size? And so I have listed there the sugar candy example. Now, if you've ever had the joy of making sugar candy, rock candy, right? You take the sugar, you make a simple syrup, and then you take the string or the stick or whatever the case may be, and you set it in that water, and those sugar crystals will start to accumulate on that string or that stick. If you want bigger sugar crystals, what do you need to add? Well, you can add more sugar, right? But you need to add more time. More time. The longer you let that solution have that sugar crystallize out, the bigger those grains are going to be. And in that molten mass, right, in that lava are all of the ingredients that we need to make different types of igneous rocks. They're all there. But they take a while to meet each other and link up. And so, if you have a very rapid cooling process, that molten material with all of those elements is going through that process of allowing those elements to meet each other and form the necessary bonds to form these minerals. They have a very short window to do so. So they form those minerals, but they do so in a really scattered way. That is, what they form are really small versions of those minerals because they don't have the time required to collect and form those very large visible mineral grains. All right, so this is a little piece of basalt. And again, you zoom in. Here's a zoom in picture of that aphanitic rock texture. We can see these little darker colored blebs in there might be some minerals that we can pick out, right? But they are really small. We had to really magnify this to be able to see that. That's what we would call an aphanitic texture. And aphanitic textures, you see that, you're going to associate that with extrusive igneous rocks, the cooling of lava. Another texture we sometimes see in extrusive igneous rocks is a vesicular texture. Vesicular texture. Vesicular textured rocks have a bunch of these little holes in them, these little holes called vugs. Lava and magma will oftentimes contain a large amount of gases dissolved in there, kind of like the carbon dioxide dissolved in your soda can. When that lava is extruded or is exposed at Earth's surface, that molten rock will start to release those gases because now that is depressurized, just like opening the lid on your soda can. So as those gases start to come out, right, as those gases come out of that molten mass, they'll do so as that molten mass is cooling. And sometimes that rock cools and hardens as that process is still ongoing. So those little gas bubbles in there end up being preserved within the rocks. And if you utilize pumice for cleaning or skincare or any of those sorts of stuff, you know that that process can produce some very sharp edges, around the edges of these holes, particularly in rocks, extrusive igneous rocks that have a lot of silica in them, a fair amount of quartz in them. you can get these really sharp edges that effectively work like kind of like the edges of glass. And so when you rub that across your skin, that's why it's able to cut away some of that harder skin callus material. That's how that's working. But what about our intrusive igneous rocks? Well, intrusive igneous rocks, they form through the cooling of these magma chambers. And oftentimes, this cooling can last millions of years, right? That is, you have a magma chamber, it forms maybe next to a convergent plate boundary. That convergent plate boundary's activity continues to fuel that magma chamber, molten rocks within that magma chamber, but then something changes. For some reason, plate tectonics goes a different route. Convergence maybe at that area ceases, and so that magma chamber, the heat source for that magma chamber, goes away, and that magma chamber starts to cool and solidify. And again, that can take a really long time. So over the course of those millions of years, all the little minerals that are forming inside of that molten mass, they have plenty of time to meet each other and link up and get really big. And the more time, that is, the more gradual this process is, the larger the mineral grains that we can get. And so a really common intrusive igneous rock texture is what's called a phaneritic texture. This is a phaneritic texture. We can see right away that that's very different from what we saw in the basalt there. This phaneritic texture, you can make out those pink colored minerals. Those are potassium feldspar. You can see some of the maybe a little clearish globs in there. That's likely some quartz. Some of the platy minerals that you're likely seeing in here are some biotites probably in there, probably some amphiboles in there as well. And we can pick those out in just looking at the sample here at, a sample that's maybe the size of a baseball or so, right? We can see that without a microscope, right? And if we magnify, we look closer, we can see it even better, right? So again, when we see this texture, right, this phaneritic texture, or a texture where we can see the mineral grains are very large enough to see without the assistance of a microscope, we know there's been some long-term cooling in the subsurface. There's been a considerable amount of time that has allowed these rocks to collect and form. All right. So to repeat, texture refers to grain size. And that grain size is going to reflect the cooling history for these igneous rocks. So typical rock textures for extrusive igneous rock, there's a whole bunch of them, but these are some of the typical ones. Aphanitic and vesicular textures, that is going to be an extrusive igneous rock type texture. That was the cooling of lava to produce those rocks. For intrusive rocks, the most common rock texture that we see is a phaneritic rock texture. And if you take a hike around the RCC campus area there, maybe the Box Springs or Mount Rubidoux or those sorts of places, you're going to find a whole bunch of intrusive igneous rocks with this phaneritic texture. It's really, really common. But then there are a bunch of unique igneous rock textures as well. Porphyritic igneous rock textures. That means that we have some big and some small. And I'm not talking like, well, these ones are kind of close, but that one looks a little bigger. I'm talking some minerals might be a few millimeters across, while other minerals, maybe you can't even make them out without the assistance of a microscope. That would be a porphyritic texture. Glassy textures. Maybe you've heard of the rock obsidian. Glassy textures form from very rapid cooling. Really rapid cooling of a lava that doesn't have a lot of gases in it will take all of the little silicate tetrahedra that are in those materials and kind of lock them randomly to where they effectively form glass. So that's really rapid cooling to make that material. The force of volcanoes can be really strong too. And so brecciated or pyroclastic materials are materials that reflect that force. That is, when a volcano erupts, sometimes those forces, sometimes the weight of the material of itself is so strong that you can take fragments of rock along with dust and ash and push all of that stuff together to when that stuff finally cools and fully solidifies, it can form a layer of rock or chunks of rock in and of itself that have this brecciated or pyroclastic texture. All right. Pegmatitic textures are really interesting too, because these things, they contain really large mineral grains. So really large mineral grains, you should be doing the math that says, okay, that must be an intrusive igneous rocks or igneous rock. And absolutely it is. These pegmatitic igneous rocks, they consist of these really large mineral grains. And so mineral grains in excess of 2.5 centimeters. And so those really large mineral grains may be mixed in with other smaller mineral grains, but oftentimes these rocks can consist of nothing but these very large mineral grains. Rocks that contain these really large mineral grains, we call those pegmatites. And pegmatites are oftentimes what you see in the museums. When you see some museum quality specimens for a lot of different types of minerals, oftentimes those are coming from pegmatites. Those are coming from these minerals that had a lot of time to cool and solidify and form these very big forms of themselves. All right, so let's take a look at a few of these things. Porphyritic, again, both large and small mineral grains. And we mentioned this earlier, that with a porphyritic texture, what that might speak to is multiple stages of cooling. If we have some mineral grains that are very large and some that are very small, right? Well, what gives there? Well, what gives is that there may have been, for instance, maybe there was a magma chamber that was cooling and solidifying very slowly, gradually, allowing some of those materials to form, some of those minerals to form. Eventually, maybe that magma chamber erupted. So inside that molten mass, maybe there were some minerals that had already formed inside of there, and then suddenly that molten material is extruded to Earth's surface. The remainder of those materials then solidify very quickly. So we'll see in these porphyritic textures, we have both these large and small mineral grains speaking to that two-stage cooling history for that rock. This is another example of a two-stage cooling history for a porphyritic rock that's pictured here. These porphyritic rocks where we can see all of the mineral grains. That is, we can see both large and small mineral grains here. We see these very large pink mineral grains, and then maybe these smaller mineral grains between them. What that sometimes indicates is a change in the cooling rate within the magma chamber. It's really interesting. Within a magma chamber, you can have some minerals, a rate of cooling that allows these minerals to solidify and get relatively big, but sometimes conditions change where suddenly the rate of cooling of a magma chamber can actually slow down. And so the rate of cooling, I'm saying that it takes longer suddenly for that magma chamber to cool fully. Sometimes the injection of additional water into a magma chamber late in its evolution can do just this, where it slows down that rate of cooling and allows some of these mineral grains to get really large. And commonly, these mineral grains that get really large via this process are these pink mineral grains here that we call potassium feldspar. Hiking in and around the Box Springs in just above UC Riverside there, you can find lots of examples of exactly this. These large mineral grains, we call these phenocrysts. Phenocrysts, P-H-E-N-O-C-R-Y-S-T-S, phenocrysts. And these large mineral grains in there, again, sometimes will be museum quality specimens of this stuff. It's pretty pretty neat. Here's the glassy texture again. If you've seen obsidian, then you've likely seen this glassy texture, and it behaves just like quartz. If you break this stuff, it'll make that conchoidal fracture. It'll make very sharp edges, something that's been utilized widely for those sharp edges. A pyroclastic texture, right, or a brecciated texture. This is what that looks like. One thing to point out here is in these pyroclastic or brecciated textures, the rocks that are contained within that mass oftentimes have these sharp angular appearance to them. That is, these big kind of sharp angular rocks that were broken up during that eruptive sequence, they end up locked together by force. And that's in part because the dust and the ash that comes out of a volcano may be solid by that point, but it's still very hot. So as that stuff settles and cools and solidifies, it'll make a pretty continuous layer of what is effectively rock. And so that rock there, that layer of brecciated materials would be considered an igneous material. All right. Awesome. And this is what a pegmatite looks like. Again, oftentimes the museum quality specimens of different minerals that you see, they're museum quality because they're very large examples of these minerals. And again, it's not because of simply the age of these materials, right? It's that they were allowed to cool over a long period of time. We let that material cool very, very slowly through time. An analogy for that would be, I love to barbecue. I'm a huge fan of barbecue. I think it's absolutely delicious. And when we barbecue, one of the most important, for those of you that are budding barbecue enthusiasts, or maybe long-term barbecue enthusiasts too, you may already know, or maybe here we'll learn that one of the most important things that you can do for the things that you barbecue is to let them rest, right? When you pull that food off of the grill, it's important to let that material rest, right? So one of the things you can do, or you can let those materials rest a few different ways. You can take those materials off and you can put them on a plate and let them sit out on the counter. Or you can take that material and whatever it is you cooked and put it on a plate and then cover that in foil, right? And let that rest that way. Or you can take that material, put it in foil, and then put it inside of a cooler and let it rest. They're all starting out, all three of those scenarios, they start out at the same temperature, right? However, that meal that you put on your counter, it's going to cool really rapidly, right? Because it's just exposed to room temperature. So it's going to cool very rapidly. That part of your meal that you put under the foil, it's going to cool, but a little bit more slowly than that material that you put just open on the counter. And that material that you put inside of the cooler and allowed to cool, or allowed to rest that way, it's going to cool very slowly. It's going to have a slower cooling rate. And that's what we're talking about here. Those magma chambers where this cooling rate is very slow, where it's going to take, it's cooling, but it's going to take a long time. That's what's going to yield these sorts of deposits. Oftentimes too, these pegmatites, to form these big, beautiful minerals like this, you sometimes need an opening in the subsurface too. Sometimes cracks or openings within the magma chamber will allow little pockets where the cooling rate is a little bit slower. And there's also the space required there for the minerals to grow in these forms. And so finding these sorts of things is a ton of fun. You can find them certainly here in California, Southern California. Sometimes we go out on our field trip classes and we find these things too. And they make some great materials to put up in around your house and that kind of stuff. It's fun. Always feel free to reach out about the field trip classes. I love discussing. Awesome. So again, I'm going to remind you that igneous rocks are ultimately classified based on first this grain size and texture. So we've got those two groups of igneous rocks. Those are intrusive and extrusive. And within both of those groups, there's a whole bundle of different rock types. And so our first job in trying to identify an igneous rock is to look at that texture first and place it into one of those two groups, intrusive or extrusive. Our next job is going to be to determine the composition of that rock. That is, what minerals are present within that rock? What's the chemistry of that rock? And this step is a special one with a really special history surrounding something called the Bowen's reaction series. And that's actually going to be up next for us in our next portion of this module. We're going to explore the Bowen's reaction series and what that tells us about the chemical composition of different types of igneous rocks. All right. So with that said, that concludes our igneous rocks discussion. In summary, igneous rocks, again, are those materials that form when molten materials solidify. And that first order of business in identifying an igneous rock is to classify that texture, identify that texture, and place that texture into either this intrusive or extrusive category. Our next step is going to begin with our next portion of this module as we discuss the Bowen's reaction series. So with that said, I am going to wish you all a wonderful, wonderful rest of your day. I'm going to encourage you guys again, if you have any questions at all, utilize those Canvas resources, get a hold of me. Let's make sure that you have this material down. I want to see you knock it out of the park, and I'm here for you. So please feel free to reach out anytime. With all of that said, again, take care of yourselves, be safe out there, and please feel free to get a hold of me anytime. All right, everybody, take care.